What part of the example did I give you yet? Did I give you the beta ij tableau? No, not yet? Okay. Okay. How about fi zeros? I think okay. Okay, the beta ij's are symmetric, so I'm just going to give you the upper portion of the matrix, and that's going to be infinity. That's beta 1, 2, 32, 49, 18 to 25, 46, 656, 900. So you've computed them already? Okay.
But I don't, my calculation for 1, 3 is 3969. I don't know, maybe yours is correct.
We'll see, we'll see. Okay, do you agree with most of...
Differs from yours for the row 3. I mean, my beta 3, 4, 3, 5, and 3, 6 is different from yours. Yes, all that line. And the one I just said.
And that one.
Yes, 1, 3.
Let's compute one of them and see what's happening. Yeah. I computed these long time ago, so we'll see how we can do this. All right, in general, to compute beta ij, you need to solve a minimization problem, say minimize z, relative to two vertices. You've got fi dx vi less than or equal to z, then fj dx vj less or equal to z, dx vi less than or equal to ui, dx vj less than or equal to uj. X is a point of the tree T. That's how you get your beta ij. Okay. So here's an example computation. For example, say 1, 2. In computing beta 1, 2, we need to use W1 and W2. So what is F1 of y? It's going to be W1. In this case, W1 is 4 times y plus H1. H1 is 0 squared. Okay? That's the definition of F1. F2 is similar. The weight is 9 y plus 0 squared. So this one will be 4y squared. This one will be 9y squared. So the problem under consideration for this one is minimize z subject to 4. Well, how are we supposed to go about this? 4 times distance between x and v1 squared is less than or equal to z. Okay? 9 times distance between x and v2 squared is less than or equal to z. Distance x v1 less than or equal to u1. 900. Sorry, 15. The next one, distance between x and v2 is less than or equal to 20. Now, if you recall, the tree was this way. So you either make the last 2 constraints look like the first 2 constraints, or these constraints look like this one. Let's make these constraints look like that, those. Okay? How do you do that? Minimize z. Well, you divide by 4, and then you take the square root. Positive square root. Is this how you did it?
No, I just looked at it. It was obvious that there was no feasible x for this problem. Because...
Oh, I'm doing the wrong one then. Yeah. Sorry, I meant to do B13. B13. Yeah, let's change this to B. Okay, yeah, for this one, okay, you're right. In this one, there's no feasible solution, because the distance between V1 and V2 is 20, 42, plus 8 is 50, but these bounds will not allow you to place anything feasibly along that path, okay? So let's look at B13. What is F3? Nine times y plus 4 squared. U1 is 15, U3 is 59. Is there a feasible solution? Yes. Did I give you a computational formula for computing beta ij? No. There's a formula. Nevertheless, let's just go with some reasoning out of the constraints. Okay, so in this problem, we're trying to solve minimize z subject to 4y squared less than or equal to z and 9y plus 4 squared less than or equal to z. Sorry, not y, but the distances. I've got these constraints.
Can we directly omit the third constraint?
Say that again.
Can we directly omit that, the third constraint?
This one? Why should we omit that? I wouldn't. No. No. Okay. Now, this one, if z is in the proper range, is equivalent to how much? Well, you just divide by 4 and then take the square root. So this is equivalent to that. Okay? This one is similar. You divide, well, you divide by 9. That leaves that. Okay. Now I've got the square here. I don't want to do it that way, just a second. Well, we're going to have to do it that way, yeah. The other ones are already what they are. So how would you solve this? I gave you some pictures before. The picture was something like this. This was the path between the two vertices, say V1 and V3. And this began at some value F0 or F10. This one's similar. So you were talking about minimizing the maximum of these two functions, right? Except that there was an upper bound for both of them. That was U3. This one's, say, U1. So you have to be somewhere here, okay? Now that feasible portion, if that contains the unconstrained minimum, you can always compute that by equating the two functions to each other and solving. If, on the other hand, this is not there, then you have to move to one of the endpoints. Yeah. So in this case, our constraints are this way. which means that my dx v1 is less than or equal to minimum of z over 4, and the other one is 50. The other one is this way. Now, you choose your z so that there will be a feasible solution to these. Okay? When you do that, what you require is, what is it that you require? You want the distance between 1 and 2, 1 and, that's a 3, sorry, v1 and v3. How much is it in our case? Yeah, 32. That's 32. You want that to be how much? Less than or equal to the sum of these two bounds. Nobody is answering anything. Did I teach you or not? If the sum of the upper bounds is less than or equal to the distance between the two, then you have a feasible solution. Otherwise, you don't. Okay? That's for tree networks only. All right, so you want the sum of that one and the other one. Now you can allow for different possibilities here, the minimum being realized by either one or the other one also. There will be 4 possibilities, and you can analyze this accordingly. But the easier way is simply to go with the picture. If you go with the picture, now the distance constraint for U1 is 15, so you go a distance of 15 units here. This is the mark for 15, value 15 from V1. U3 is 59. So it's not actually a constraint, so U3 actually includes the entire path here. So I'm not going to do that, but you want to stay in this portion. Okay? Now when you plot the first function, this one, what is the value at 0? It's 0. And then it goes quadratically. It goes something like this with a rate of 4. Okay? This is 4y squared. And at this point, what is the value? I don't know. You can compute it. 4 times 15 squared. Okay? Is that 900? Yeah. Okay, so the level you've got here is 900. The other one, what is the other one? At y equals 0, it has a value of 16 times 9. How much is that? 144. And then as you move, you go something like this, except that you go much faster, I think. So this is 9 times y plus 4 squared. This time y is measured, let's make it y prime. Y prime is measured from here, okay? All right, so at 15, what's the value? 3969. Are you sure?
Yes.
What was the entire distance here? 32?
Yes.
So this portion is 17.
17 plus 4.
So 9 times 17 plus 4, which is 21 squared. 9 times 21 squared is how much? 421? 41, okay. And that gives you that much, huh? Okay. Okay. So what am I supposed to do? This is the function. Of course, I have to take the value at 15. That's the best I can do. So my beta value is this much. See? The other one is too complicated. You can do it, but this one is much easier. All right, so did I make a mistake or not? I guess I made a mistake. 3969. I have no idea how I computed it. I computed it about 28 years ago, so I don't remember. Okay. This was a good refresher for myself also, because a long time ago I computed these things, and of course it's possible to make mistakes, numerical mistakes. And anyway, that's what we've got. What about these guys? If these are all incorrect?
2, 3, I believe, is 684.
2, 3.
684, that's what I calculated. But
6084, huh? Let me write those in red. You guys can check at home, okay? So what was my number? Because I'm going to have to use my numbers. Maybe otherwise things will be difficult. What was the old situation? 3249. Maybe I changed the data along the way. Maybe that's what happened, you know. But let's see. This is 3969. Tell me this one.
6084.
This one?
Those are correct.
Okay.
Equal to mine. The row 3 is 576.562. 576, 5076, point 562.
5776.
Yes, 5076.562.
Let's make it 56.
First part is not as
I think I probably used the wrong data. I probably changed something for number 3. Whatever. This one?
35, 12,416. 12,416.33.
This one?
1,024.
That's it? It's only number 3 that's different, so obviously
It was related to number 3 is like there's something.
I wonder if my HI were 0.
The HI is 4.
Yeah, I know. But when I computed this, was it 0, I wonder? whatever. Okay, let's go with the red numbers, okay? Because you seem to have done this correctly.
I think the forecast there is not written correctly. As is
Which one is correct?
57 is not set.
Which one is correct? Is one of them correct? The red one is not correct, but is the black one correct?
Not, you didn't write as he said.
Oh, I see. That's what you're saying. What did you say again? 5776.56. Huh?
34 is, that's what I calculated, is 5,076, 34.
5076, I see.
5,076.562.
Okay, let's just go 2 digits, okay? 5076.56. I changed it because I had a 7 in place of 0. Okay, let's just go with these numbers. I thought this example would be easy, but it's quite complicated actually. Okay, we'll just solve the threat problem, the dual problem, by inspection. Okay. Later on, I'm going to tell you how to solve it algorithmically. Does everybody have the dual graph? The dual graph is just the beta ij values on the arcs and fj0 values on the nodes. Okay. And what was the dual g function? Minimum or maximum? Maximum of alpha k, beta k. What's alpha k? It's the maximum fj0, j restricted to k. And what is beta k? Minimum beta ij, I and j in k, I less than k. I less than j. Okay? And beta ij is defined as I've given to you before. All right, so for p equals 1, what is the optimal solution to the dual problem? What am I supposed to do? You look for p plus 1, two elements, in this case p equals 1, so you look for two element subsets of the vertex set. Okay? So, for example, if you pick this one, is that optimal or not? Well, the value associated with 2 and 3, so if you take your k to be the vertices 2 and 3, just as an example, in that case, the g value for this case will be the maximum of two things. The alpha value, what is the alpha value here? 0, 144, so 144. That's the alpha value. You take the larger of node values. What is the beta value? There's only one beta under consideration, so it's that. So this has the value 6084, but I'm trying to minimize this function. So in my optimal threat, this is probably not the best choice. Which one is the best choice?
It could be 2, 4.
1, 4?
2, 4.
2, 4? 2 and 4. Yeah, 2, 4 seems to be the best choice. Okay? not true.
Could be. One six. No. A infinity B maximum.
There's no feasible solution to the one-centered problem. The primal problem with one facility does not have a feasible solution. Why? Because the index pair 1 and 2 does not permit a feasible solution. The strings, remember, don't reach each other. So there is no feasible solution to the one-centered problem, meaning the primal one-centered problem, because of infeasibility, we defined its optimal value to be infinite. Okay, that's a minimization problem. And so for this dual problem, you have the same value, which is infinity. I picked the largest because I'm trying to maximize it. Actually, I told you incorrectly. We're trying to maximize the g function. Isn't that right? We're trying to maximize the g function, and so the maximum is obtained by that. Okay? You could immediately read it off the graph. That's the best. Okay. What about p equals 2? What am I supposed to do?
You will look the maximum. How can I explain that?
Well, first of all, forget the maximum. What kind of entities am I supposed to look for? How many vertices? 3. I need 3 vertices. So I need to look at 3 vertices at a time. So if you pick a possible solution such as 1, 2, 3, for example, just as an example, what am I supposed to do? I need to look at the maximum, so 144. So when k is 1, 2, 3, the g value for 1, 2, 3 is going to be the maximum of 144, which is the alpha value for that. And then the beta value will be how much? The smallest of them. 3969. We'll try to maximize this g value computed in this particular way. Okay? If you ignore the alpha here, if you assume alpha is sort of, well, in this case, alpha is actually the largest alpha in our problem is smaller than the smallest beta. You can see that. So alpha can be ignored actually in our problem. Okay? For that reason, we're trying to find a 3-clique whose minimum arc is largest. Which one is it? That one has 900. Is that a good choice? What about this guy?
1, 2, 3 seems good.
We're trying to maximize the smallest arc.
154.
154.
5, 6, 4.
5, 6, 4. I've got that, this, and this. 3600 is the smallest. To me, it looks correct. Yeah. I don't-
135? 135%?
What about?
135?
Well, there are alternate solutions, but 3600 is the best you can do.
For 135?
Actually, according to my old data, so maybe things might have changed now. Let's see, I have the following ones listed as possible alternate, optimal solutions.
here?
Just a second. Let me write down, because you know, I did this for my old data. If there's something incorrect, we'll just do it. Okay. This is according to my old data. Since I have an incorrect row in the beta computations, maybe I need to revise this.
Things have changed because of 1, 3.
What about 1, 2, 5? 1, 2, well, anything that doesn't involve 3 should not change, okay? What about this guy? How much is that? 2, 3, 5. 2, 3, 5. Well, I've got 3,600 for that also.
1, 2, 3 is the best net because its value is changed.
Oh, I see. 1, 2, 3. So this.
Old data,
Yeah, okay. Okay, so I erase this. It looks like we've got 1, 2, 3. And the value is 3969. What else? 135. Because this is still the smallest. That arc is being shared by a number of 3 cliques. So let's just list them all. 135. What else? Anything else? 134. Yeah. What else? How about 136? Well, 13 must be there. 136, you've got that one, which makes you lose, actually. Anything else? Involving 13, that's the best we can do. Okay. What about the optimal p-center objective value? It's that much. How do I know? Because I know the primal and dual optimal objective values are equal. I haven't proved it yet, but we'll prove it. Okay? And I know also that in the optimal 2 centers, 1 center will be allocated to the 1, 3 pair, and it will optimally locate in such a position that the objective value will be the same as the beta value. And that point, the remaining one will be located somewhere else, okay? But then that point, that solution will be feasible. We'll see how that works out. 3. I have to revise everything, so you tell me now. Wow, we're out of time already. Esra, you tell me the best for-click here.
Possibly 3,600.
3,600, yeah. I also guessed that. Is 3,600? Let's see, can you form 3,600? Well, 164. Are you sure? No, I need 4 elements.
1, 2, 3, 5 gives 3969.
1, 2, 3, 5.
Gives 3600.
1, 2, 3, 5. 1, 2 is infinite. 1, 3 is 39. 1, 5 is that much. 2,3 is this much. 2,5 is 3,600. 3,5 is that much, yeah. Well, it's the next smaller value than 3969, so there's a clique that achieves that. There might be one more. 1, say 1, 3, 4, 5. 1, 3, 1, 4, 1, 5. Okay, that's 3, 4, 3, 4, 3, 5, 4, 5, 4, 5. Where is that 4, 5? Yeah, that one seems to also qualify for 3,600.
They are the combinations of various elements.
Well, could be, but in general, there do not need to be any relationship between those and those. Okay. Anything else or any other combination? Four you can do, 5 you can, well, let's do 5 together. When you have 5, you've got a 6 clique. There's only one 6 clique under consideration, and its smallest arc is 225. So the solution is obvious in this case. Say that again.
For P is equal to 4 solution, we will exclude the 2-4 combination. So either 2 will be included or 4 will be included.
Okay.
900. That's
Well, again, my numbers are different, so I can't do it here. 900.
1, 2, 3, 5, 6. 1, 2, 3, 5, 6. 4. 1, 4, 3.
Just a second. How much is the
900.
cost? 900. Could be. Another one?
1, 4, 3, 5, 6.
This one is also 900, huh?
Yeah, I hope so.
Okay. Anyway, for small problems, you can do this by inspection, even though we have pretty complicated functions here. But the important thing is to know how to compute these beta ij's, okay? So make sure you know that. You have a comment?
P is equal to 3, 2, 6, 4, 3. Okay.
If 2 and 4 is together, 2, 3, 400.
Yeah. You compute, you look at the beta value for each one. And then you want to make sure that each such beta value is greater or equal to 3,600, okay? If you have something smaller, then you're not optimal.
Can we evaluate on this chart is not is memorizable?
Say that again. Can we evaluate?
Can we see that pairs or that sets on this chart?
I guess you could, yeah, because that graph is nothing other than this chart, actually. This is just a table. That's a graphical way of visualizing the same thing. So you can certainly do it here. I'm not very good with tables. I work with graphs. It's much easier for me. But you can do it anyway, yeah. Okay.